I'm going to start the recording here. So this week we are covering chapter 6. Chapter 6 is a lot of information, but we're slowly getting more into how we use physics in applications of ultrasound. So maybe some of this stuff will start to piece together a little bit more for you guys. Remember, everything is like an onion. We're kind of peeling back every layer when it comes to ultrasound physics. So as we know, sound is very particular. There's certain parameters that we need to follow. We've learned all about that in the previous weeks. But now we're going to be talking about how sound behaves, particularly in media. So we're going to be focusing the majority of this lecture on soft tissue. We will kind of touch base on just sound traveling through other types of media, but we're really focusing on how does that sound behave when it's traveling through human biologic tissue. So as we already know, sound is going to travel through the body and it moves from one medium to another, right? So if we think about when we're scanning and we put that transducer down, the first thing that sound wave is going through, if we're doing a transverse midline abdomen, is going to be the skin and then the soft tissue, and then we hit the pancreas, right? And then we have our vessels and then our spine. So we're sending that sound wave and we are expecting it to travel and transmit itself through all of these different layers. And as it's doing that, it's moving through one medium into another. So we're going to talk about what happens to that overall strength and composition of that sound wave as we expect it to travel through these different types of medias. So a portion of our sound is going to reflect at the boundaries between all of these different structures. And in ultrasound, we love reflections. And we're going to learn about why in a few slides. These reflections are how we compose our images. If it weren't for reflections, we wouldn't get anything back in order for our system to process. So the remainder of sound as it's traveling is going to continue traveling deeper into the body until it hits that next medium boundary, right? So we're expecting that sound wave to continue traveling, but as it's traveling through these different medias, it's sending back these reflections to us, and we'll learn all about that process today. And as we know, sound, of course, is naturally going to weaken as it travels. So some terminology here, you guys are, pretty aware of all of this stuff, but just to reiterate, when we're talking about propagating or propagation, we are talking about sound traveling through tissue. We are also learning about reflections today. So this is the portion of the sound that is going to reflect off of medium boundaries. We're going to be learning about receiving reflections, attenuation. What does that mean in terms of our sound wave? How does it weaken as it travels? And then anytime we're using the term amplified, we're talking about our ultrasound system that is kind of artificially strengthening the reflected sound waves as we receive them from the transducer. We're going to get more into amplification in the next few weeks, but we're really going to be talking about propagation, reflection, and attenuation today. So our signals, right? Here is this overall breakdown of this process of sound waves creating these images, right? Our first step, our sound waves are going to be created and sent into the body by our ultrasound system and our transducer. The sound waves are going to attenuate as they propagate. So as they travel, they are going to weaken. Then the sound waves are going to be reflected at specific boundaries between two different types of media. Those reflected waves are going to be received by our transducer. The waves, once they are in that transducer, are going to be converted into an electrical signal. So we're taking acoustic energy and we're turning it into electrical energy in our system. And then that signal is going to be sent into the ultrasound system to be amplified in order to be displayed on our screen. So today we're really only going to be talking about steps 1, 2, 3, and steps 1 through 3. We're not really going to be getting into what happens in the transducer and in the system until a little bit later on. Now, decibels are going to be very important. Originally, when we think of sound, prior to any knowledge that you had for ultrasound, you've probably always associated decibels with sound, right? That's how loud something is. And then we've kind of learned about hertz and all of these other units that we give to describe those parameters of sound waves. But now we're kind of taking a step back and we're going back to that overall strength of those sound beams, right? How loud something would be if it was audible sound. So we want to make sure that we are measuring our strength of our sound waves especially as they're traveling through tissue, right? Because that strength is going to weaken over time and over distance. We need to quantify that number, and we need to quantify that strength. And we do so by, a few different ways. We do it mainly by decibel notation, and we use logarithms to do that. Now, logarithms do not give us precise, absolute, accurate numbers, right? There's no scientific equation for us to get a precise numeric value. We're looking at the relative change. So we're using, an increase and a decrease to help us figure out the overall change in that strength of the sound wave. We're not looking at, a particular number going into decimal places. It's not that type of scientific precision. So decibel notation is a relative measurement, as we said. It's a comparison, right? So we're comparing our end value to our original value. We can annotate that in a ratio, and we also do it by logarithmic representation. So let's talk about decibels a little bit further. We are going to talk about logs in a second. You guys may remember that from some of your math classes. You may not. But decibels, we are reporting that relative change, right? So was it a positive change? Did that sound beam get stronger or larger? Or did it get smaller and weaker, a negative decibel change? Now, of course, in ultrasound, we're not really looking at a sound wave getting stronger. So we're typically going to be reporting a negative decibel change. Now, how do we do that? What does that mean, right? So when the intensity of our original sound wave is reduced to half of its original value, that relative change is going to be marked by -3 decibels. So it's a kind of bizarre number, but that's pretty much the scientific and the mathematic value that we've given to ultrasound ranges traveling through human tissue. So if we have a 3 decibel change, this means that our strength of that sound beam doubled over that particular period of length or time. If we have a -3 decibel change, that means that we have half of its original value. So just keep that in mind. Again, we're not looking at, perfect, precise numbers with this change. We're not looking at a particular equation with this change, but just be aware that 3 is going to be that magic number. Next, we have logarithms. So this is a method of rating numbers. Little different than that scientific shorthand that we learned last week. This, we're kind of looking at the overall increase or decrease in that original number when we're talking about these really large numbers or these really small numbers. Scientific shorthand and scientific notation, we have a precise number that we need to shorten, right? Logs, we don't have that precise number. We're looking at something and how it changes by tenfold. Okay, so when we have a log that has increased by 2, that means that value has actually increased 100-fold. So we look at our examples, the log of 1,000 is going to be 3. The log of 10,000 is going to be 4. 100,000, 5. So a simple way that you can remember that is just look at your zeros, okay? How many 0 places do you have? And that's going to be your log. Now, of course, if we have a really small number, that log would be a negative, right? But we're mainly working in terms of 10. Moving into attenuation. So now we're getting into some of the things that we've talked quite a bit about. We know attenuation is our decrease in those 3 bigness parameters of our sound wave as it's traveling through a medium. So our power is going to decrease, our intensity, our amplitude is going to decrease, and that is just a natural process of those sound characteristics. We are going to report this change, this decrease in power, in decibels, right? So again, we're going back to that relative change. We're not looking for a precise numeric value. Our overall attenuation is going to be determined by 2 factors, and we're going to come back to this quite a bit. We're going to talk a lot about attenuation today. But our path length and our frequency of sound. So how long, how great of a distance do we expect that sound wave to travel? Of course, the longer we expect it to travel, the more attenuation is going to occur, right? The longer we want that sound wave to travel into the body, the more it's going to decrease in power. So if we have an increased distance, we are going to have increased attenuation, which when you think about it means a decrease in power. So don't be confused with what attenuation actually means. Attenuation is a decrease in power. So if we have increased attenuation, that means we have less and less power of that sound wave. Same thing with frequency. So frequency is directly going to affect that attenuation. Think of when we're using the 12 megahertz transducer, that high frequency transducer. We don't get as much depth into the body with that, right? So we are having a massive amount of attenuation when we have these higher frequency sound waves. Now, if we want to look lower into the body, think of what I have you guys do with that curved transducer when you're looking deeper into the body, right? We're adjusting that frequency. If we need to see further into the body, we're lowering that frequency. So keep that in mind as we move forward through this PowerPoint. So attenuation also has 3 processes that contribute to the overall attenuation, and that is going to be our reflection, our scattering, and our absorption. And we're going to talk about each one of those. Before we get into reflection, here we can kind of see how differently a high frequency sound wave behaves in terms of attenuation versus a low frequency sound wave. When we're looking at that high frequency signal on the left side, we see how quickly it attenuates, right? And that's because we are putting all of that strength and power into the initial composition of that wave. Now, when we have a lower frequency signal, this still looks like a pretty high frequency signal to us, but it is definitely a lower frequency signal compared to the image on the left side. It can propagate for a longer distance before we're reaching that same level of attenuation. So moving into those 3 processes that affect attenuation, our first is going to be reflection, right? We love reflections. This is how we get our images. As we previously said, this is when a sound beam or wave reaches a boundary in the body, and a portion of that wave's energy is going to be reflected back to the sound source or our transducer. Now, reflection is going to weaken the portion of the wave that continues traveling through the rest of the body. So as we said, that sound wave, it's still traveling through, right? But as it's hitting those boundaries, a portion of that sound wave is being reflected back to us. A portion of that sound wave's energy is being reflected back to us. And that's why it weakens over time. As it's continuing traveling, it's sending back reflections. So little pieces of that original power and intensity are getting sent back to us, and it's creating that sound wave to become weaker and weaker as it continues traveling forward. Now, we have 2 forms of reflection in soft tissue, and we'll talk about each of these. They are going to be specular reflection and diffuse reflection. Now, specular reflection, this is like in a perfect world, we would have specular reflection, but ultrasound is not perfect. The human body is not perfect. So specular reflection is not something that we are seeing in clinical ultrasound. We are using diffuse reflection to create our images. So what is the difference between these 2 types of reflection? Specular reflection is when we have our boundary and that sound wave hits it, that boundary is smooth. There are no lumps, there are no bumps, right? There are no inconsistencies in that boundary. Unless you have a metal prosthetic in your leg, that would be the only smooth boundary in our body, right? So we're not really looking at specular reflection in our profession, but we need to know the difference between these 2. So diffuse reflection is going to be our boundaries or our interfaces that are not smooth, right? They have lumps, they have bumps, they have grooves and divots and all of that. So how do we expect sound to hit that boundary and come back to us? When we have specular reflection, right, our smooth boundary, the sound wave is only going to reflect in one direction because that boundary is smooth. So we have our original sound wave traveling to this smooth boundary. It hits that boundary and it's going to travel in an organized fashion, and it's going to travel off in only one direction. Okay, so think of like like a military, like those people training in boot camp, right? They're walking in sync. They're all going in the same direction. That would be specular reflection. Now, if we send in our sound wave directly perpendicular to that smooth boundary, it's going to reflect directly back to us with specular. If we send in that original sound wave and it is coming in at an angle other than perfectly perpendicular, so it's off axis by any means, that reflection is going to hit that original sound source is going to hit that smooth boundary, and it's going to reflect off at a matching angle in the opposite direction. So we're going to learn a little bit more about that as well, but that means that that would not travel back to our transducer. So if we were operating with only specular reflection, we would have to send our sound beam in to every single boundary and interface at a perfect 90-degree angle to get any reflection back. So think of a mirror. When you're standing right in front of a mirror, you see yourself. That reflection is coming right back at you. But if you're standing to the side of a mirror, you can still see the mirror, but you no longer see your reflection in the mirror. Okay? Diffuse reflection, it's accounting for those lumps and those bumps and those imperfections in that boundary surface. So our original sound wave is going to hit this irregular surface, and that reflected sound wave is no longer going to travel in one direction in an organized manner. It's going to travel off into different directions as it's interacting with those lumps and those bumps. So all of those irregularities are going to create a different angle of reflection, and we are going to be able to catch some of those angles of reflection back into the transducer. So that is why we need diffuse reflection, and that is how we create our images. We're going to learn a little bit more. We're going to kind of build upon this concept. So here we have just a nice diagram showing the difference between how a sound wave would interact with these two different types of surfaces, right? These two different types of reflection. So see, with our specular reflection, if we had our sound wave coming in this way, perfect angle with that smooth border, it would reflect right back to us, and we'd be able to create images with that. But because we're sending in our original sound wave on an angle, it's matching that angle in a different direction, and therefore would not come back to our original sound source with this angulation. With diffuse reflection, we can capture some of those reflections from that irregular surface. So we don't need to be perfectly perpendicular with our surface because of diffuse reflection. So we can come in on an angle and still be able to get some of these reflections back to process into an image. Now, we wouldn't get these, right? Because that angulation is too far out of our original pathway. Okay, another type of process that is associated with attenuation, we have scattering. Now, scattering is a type of diffuse reflection. So this is still in that ballpark of diffuse reflections, although it is considered its own process of attenuation. So when we have scattering, this is when that sound beam interacts with a tissue interface that is very small. And when it does that, it's almost too small that the sound beam gets a little bit confused, and it's traveling off in all of those different directions. So it's very similar in concept to diffuse reflection, but now instead of talking about just an irregular surface, we're talking about a small tissue interface. Higher frequency sound waves are going to scatter more than lower frequency. Kind of think of like if somebody stops short on the highway, the faster you're going, the less time you have to react, so you may potentially spin off, right? But if you're traveling slower and somebody stops short on the highway, right, you have a lower frequency, you have more time to react to that and to continue traveling in your, dedicated pathway. Next, we have Rayleigh scattering. Collaborate just doesn't like me for some reason, but this is an organized form of scattering. So we had an organized form of reflection, which was specular reflection, but now we have an organized form of kind of diffuse reflection and scattering. This happens only when the dimensions of the sound beam's wavelength, so when the diameter or the distance of that wavelength is larger than the structure that it's interacting with. So we know sound waves really small, right? We're not seeing sound waves. They're very small, but we also have components in the human body that are smaller than that wavelength distance. So say the diameter of a red blood cell is smaller than the wavelength of the sound wave, then we are going to have Rayleigh scattering. So this is going to be seen more with a longer wavelength, right? So when you have a shorter wavelength, a higher frequency, we're not going to be seeing it as much. So Rayleigh scattering, a very physical principle type of thing. We're not accounting for this when we're scanning. It's not something that we're really taking into consideration, but it is something that you need to know for your registry. Next, we have absorption. So we've done reflection, we've done scattering, and now we are talking about absorption. So we are talking about how sound travels through human tissue, right? So a natural process that happens when we're converting different types of energy is our bodies naturally convert different types of energy into heat. So that is when we are taking into consideration the interaction of the sound waves energy with our biologic tissue, and our biologic tissue takes that sound wave energy and it converts it into heat, and we expel that. Obviously, we're not feeling that. We don't feel warm when we're getting an ultrasound, right? So this is on a very microscopic level, but we do need to take that into consideration when we are thinking about the overall attenuation of our sound beam. So the tissue is going to react to that. And this is also why we are a little bit more concerned with the overall power of the sound source when we are looking at fetal ultrasounds. Fetuses are very receptive to changes in heat. You can't take a hot bath, you can't go in a hot tub, you can't go in a sauna, you can't go tanning, because the fetus is very receptive to any increases in heat, and that's why we try to limit ultrasounds as much as possible, and we have these safety regulations in place for that reason. But just the regular person, we don't really need to worry about that too much. It's all going to be within the normal, safe, healthy range. But we do need to take that into consideration when we're trying to calculate how much weakening of our original sound beam is happening. So absorption is going to be directly related to frequency. So increased frequency is going to heat up more tissues. So that is going to have us have more absorption. How much of that sound waves energy are our tissues actually absorbing? Next, we have our attenuation coefficient. So we've talked about attenuation, we've talked about the three processes that contribute to attenuation, but now how do we start to kind of put all of that together, right? What does that mean in terms of our scanning? So attenuation coefficient is the process where our sound waves energy is actually going to be calculated by that absorption, scattering, and reflection. We're taking all three of those processes into consideration to give us the overall attenuation. When we're talking about overall attenuation, we're asking the question of how much attenuation has occurred in 1 centimeter, right? So how much attenuation is occurring given this length that we are expecting that sound wave to travel? Now that total attenuation is going to depend on, of course, the frequency of that sound wave, as we said earlier, the distance that that sound wave traveled, and the tissue that we sent that sound wave through. Every tissue is going to behave a little bit differently. So yeah, we're kind of talking about just normal biologic tissue, but our liver tissue behaves differently than our kidney tissue. Our fatty cells behave differently than our muscle cells. So we need to take all of that into consideration when we're talking about that overall weakening or decrease in power of our sound wave. We can actually calculate the total attenuation in decibels by taking our attenuation coefficient and multiplying it by our distance. So our attenuation coefficient is just that relative change of decibels that occur when that sound travels 1 centimeter. And this is information that if they were to ask you this on your registry, you would be given some type of information in order for you to calculate either that attenuation coefficient or that total attenuation. So here we have another kind of equation that you would be responsible for on your registry. Now, we are always kind of talking about sound waves in soft tissue, but particularly we're always kind of talking about how sound waves behave, but particularly in soft tissue. So when we have a given frequency, right, we know the frequency that our sound wave is traveling at, that's going to be given to you. You can divide that by 2 and get a general attenuation coefficient in soft tissue. So you need to remember that with that, that is talking about, the original attenuation rate. Sound is going to weaken as it travels, so that is going to ultimately change that attenuation coefficient as it progresses further into the body. So higher frequency waves are going to lose more energy than lower frequency waves do. We pretty much know that from previous lectures at this point. If you want more information on how you can calculate the attenuation coefficient in other types of mediums, that's on page 86 of chapter 6 in the textbook. So mainly for me, you just need to know how that attenuation coefficient is going to react in soft tissue. Next, we have our half value layer thickness. And thickness can be a little bit confusing, and we'll get to that when we get to our little diagram, but it's mainly talking about distance. So the distance that our sound wave, our original sound wave, needs to travel through a tissue until it reaches the point where its original intensity is 1/2 of its value. So say you have an original intensity of just 100, right? How long of a distance did that sound wave have to travel until it reached 50? Okay, so we're looking at that relative change, we're looking at that distance. So the half value layer may also be described as the depth of tissue that results in 3 decibels of attenuation to the intensity. So that should really be -3 decibels of attenuation to the intensity, right? That negative change, we want to see that decrease in intensity, that negative relative change. So this is going to be measured in units of centimeters or any given length, right? We're talking about thickness, we're talking about how long it has to travel until it reaches that half value point. This is going to depend on 2 factors. Of course, the frequency of sound is going to have a factor on that. A higher frequency is not going to take as long to travel to get to that half intensity versus a lower frequency one would. And then also our medium. So this is kind of going back to that density and that stiffness of a tissue that is going to play a role in this. If you have a tissue that is not stiff, not dense, right, it's going to be able to travel longer, a greater distance. If you have a very dense, very stiff tissue, it's not going to be able to travel as long until it reaches that half value of intensity. So here we have our diagram. You can see that this would be our original sound source coming in here. So you can see that it's taking a specific distance through the tissue to get to that half intensity of the original wave, right? So that would be given to you in units of distance. You would be able to look at a diagram, use those clues to help you figure out what they are asking you. Now, when you have a thin half value layer thickness, right, or a short, if we're talking about distance, right? So don't get confused. Thin is also going to equal short half value layer thickness. This is going to be produced by a high frequency wave, right? That higher frequency is not going to be able to travel as long until it reaches half of its power. Also, any media with a high attenuation rate, so those thick, dense, stiff components or cells, muscle, fibrous tissues, tendons, ligaments, bones, all of that. Now, a thicker or a longer half value layer thickness is going to be with a lower frequency wave or with a medium that has a low attenuation rate. So fluid is easy for sound waves to travel through. Fat is easy for sound waves to travel through. So that's going to have a greater half value layer thickness than traveling through, a muscle layer. Next, we have impedance. So impedance, again, is kind of talking about that overall density of a medium and how that's going to affect the sound wave traveling through it. So this is the overall acoustic resistance to that sound wave traveling in a particular medium. We can calculate this by multiplying the density of that medium and the speed of our sound beam, and that will give us that overall resistance for that particular medium. This is going to be measured in units of rails, and it's represented by the letter Z, which is kind of different from what we've learned. This is going to be determined by the medium only, right? So we're talking about the overall resistance in a medium, so of course it's only going to be determined by that composition of that tissue. The reflection, depending on these mediums, is going to be represented by the differences in acoustic impedances of the surrounding structures. So what does that mean, right? Our liver is going to have a different impedance than our right kidney. Our soft tissue, skin, and fatty layers are going to have a different impedance than our pancreas. So as we're sending that sound wave in, we're expecting that sound wave to travel through these different layers of media. We need to be aware of how much resistance each of those layers is putting up. And that's going to really affect the reflection that comes from that boundary between those two different resistances or those two different mediums. Next, we have our incidence. So this is talking about how we're sending that sound wave into the body. Okay, this is talking about geometry. So the angle that our original wave is hitting a boundary is going to determine the behavior of how the rest of that sound wave travels through those additional layers. So we're looking at, are we coming in at a normal incidence? Normal incidence is always going to be a right angle, so you are perfectly at 90 degrees. Or are you coming in at oblique incidence? Are you coming in at an angle that's slightly off of that perpendicular 90 degrees? In a perfect world, we want a right angle, right? That's going to mean that the more reflections we get back from that interaction with the boundary, whether it be specular or diffuse. So we want to be as close to a 90-degree angle of incidence as possible. But as we know, the human body is not perfect. We need to have some of these degrees of angulation in order to get our sound wave into the body. So we want to keep in mind that we want to be as close to 90 degrees as possible. This is why I'm always telling you guys to look at your hand. Be perpendicular with the structure that you are trying to look at. This plays a really big role when we start to learn vascular in the fall. So just kind of keep that in the back of your mind. So what does this angle of incidence mean? What does it look like? Well, our diagram here on the right side, this is a example of specular reflection, right? Because we're looking at a mirror, smooth boundary. So this is not really something that we are referring to too often in clinical ultrasound. So our incident ray is going to be our oblique incidence, right? Our original sound source. So as you can see, we're kind of coming in on this, I don't know, say 45-degree angle. So we're not coming in at normal incidence. We're not coming in at a right angle or a 90-degree angle. So we're sending that sound wave into the body. It's hitting that smooth boundary. And as we know, when we have specular reflection, it is going to travel off in an organized one direction fashion. So that reflection is going to travel off this way, and it's never going to come back to our transducer here. When we have normal incidence, we're coming in at a perfect 90-degree angle, we're sending that in, we're hitting that smooth boundary, it's going to come directly back to us. Again, does not happen in ultrasound. So we're always kind of working with oblique incidence. We're always looking at our angle of incidence in order to help us kind of calculate that and calculate how that wave is going to behave as it's traveling through that boundary. So normal incidence, this is when our angulation of the sound wave is hitting the boundary at exactly 90 degrees. Oblique incidence is when we are hitting that boundary at anything other than 90 degrees. Okay, so how do we piece all of this together? How do we talk about what has happened to the sound wave as it meets the boundary and what is going to happen after that sound wave travels through that boundary? So we are looking at the overall intensity of these components. So the incident intensity, right? That original sound wave intensity, the reflected intensity, right? How much is left over after our reflection has occurred? And then our that's transmitted intensity. How much is left over after that reflection has occurred and is continuing to travel forward? Reflected intensity is how much intensity is being sent back after that reflection occurs. So this is where our loss of power is going to come in, and we need to be able to be aware of that in order to determine how it's going to continue behaving, right? So how does it come back to our transducer? What is that strength as it comes back in our reflected intensity? What is the strength as it continues traveling forward to the next boundary? So we do that by these additional coefficients. So we talked about attenuation coefficient, how much sound beam strength is being attenuated given a particular distance. We're now looking at the intensity reflection coefficient and the intensity transmission coefficient. So intensity reflection coefficient is what percentage of that intensity was sent back to the sound source and the transducer after it hit that boundary. So clinical ultrasound, very little intensity gets reflected back, but we need at least some reflected intensity to create our images. Okay, so the majority of our sound beam is going to continue traveling forward. So our intensity reflection coefficient is usually going to be a small number, right? A very low percentage. Now, a greater percentage of the sound wave's intensity is going to be reflected when we have different impedances between two medium that are very drastic. So when we have a bone in our picture, or we have lung in our picture, the difference between, so when we're looking at our transverse midline abdomen, we have the skin, soft tissue, pancreas, great vessels, and then our spine right underneath it. The difference in impedances between the layer of where our great vessels are and the layer where our spine is drastic. And that's why we get that crazy dropout of our of the area of our spine, right? We can't evaluate it. It just shows up as shadowing. And that is because the majority of that sound wave, once it hit that in that boundary between those two very different impedance mediums, it all got reflected back to the sound source, right? None of it traveled through because it can't travel through that impedance of that bone. Now, intensity transmission coefficient is talking about the percentage of that intensity that's going to continue traveling forward even though it's already hit a boundary between two media. So this is going to be a pretty large percentage. So about 99% of the sound wave's intensity is going to continue traveling even after that sound wave hits a boundary. So the smaller percentage of a sound wave's intensity is going to be transmitted between large impedance mediums. So same thing, soft tissue and bone, we're going to have a very small intensity transmission coefficient at that impedance or that boundary between soft tissue and bone because it cannot transmit through that bone. Right? So that transmission percentage is going to be very, very low, whereas that reflection percentage is going to be very, very high. Okay, so back to kind of our normal incidence, right? So this is going to, again, play a role on how that sound wave behaves after it reaches a boundary. So reflection is very important when it comes to normal incidence. This is when we have that perfect 90-degree angulation, and reflection is only going to occur if the media on either side of the boundary have different impedances. So if you have a soft tissue and a soft tissue that have the same impedance, right, that have the same resistance to them, reflection is not going to occur if we're hitting it at a 90-degree angle. It's just going to keep on traveling, right? Because there's no boundary, there's no like bump in the road for it to be reflected back. It's going to keep on traveling if we have normal incidence coming in at a 90-degree angle and our two media have the same impedance, the same resistance. We want to have a difference in resistance to get these reflections. So a percentage of that incident beam that is reflected is related to the difference in tissue impedances. As we said, no reflection is going to occur if the two tissues have the same impedance. That sound wave is going to keep traveling. A small reflection will occur if the impedances are different but close, and then the larger reflection is going to occur if the impedances are significantly different. So like we said, that soft tissue in that bone, those impedances are drastically different, so we're going to have a really large intensity reflection coefficient. A large reflection is going to occur at that boundary because of those drastic impedances. As for transmission, a percentage of the intensity that continues to move forward when the beam reaches a boundary between two media. And of course, with normal incidence, all of the sound wave is transmitted when the tissues have the same impedance. So if you have soft tissue, they have the same exact impedance, you're coming in at that 90-degree angle, that wave is going to continue transmitted and none of it's going to be reflected back. Now, when we have oblique incidence, so this is mainly what we're going to be working with, reflection may or may not occur depending on that degree of angulation at the boundary, right? So if we're coming in on an angle, we're sending that sound wave in on an angle, when it reflects off, it may not come back to us. So we may not get a reflection to process. So our reflection angle is also going to be equivalent to our incident angle. So you're going to hear those terms interchangeably on tests and on your registry. Now, transmission with oblique incidence, again, this may or may not occur depending on the degree of angulation at that boundary. If transmission does occur, it may travel in a straight path or it may bend or change direction. So this is known as a concept of refraction, which we'll talk about that in a second, and it gives it the kind of quote unquote appearance of bending, but really what it's doing is it's changing direction. So we'll talk about that. We'll talk about that actually in, I think, our next slide. But oblique incidence, right, in terms of reflection, let's talk about it a little bit further. So conservation of energy, this is going to be the sum of both the reflected sound wave and the transmitted sound wave, and they have to equal 100, right? We have to account for all of that sound wave. So 100% is going to equal our reflection coefficient and our transmission coefficient added together. You may have a reflection coefficient if you're going from like kidney, if you're going from liver to kidney, well, you have two soft tissues, but they have different impedances. Your reflection coefficient may be 20%, but your transmission coefficient is going to be 80%, and that's great because it equals 100. So our IRC and our ITC have to always equal 100% to account for all of that energy of the sound wave. We can calculate that a little bit further. So the sum of reflected sound intensity and transmitted sound intensity must equal the incident intensity. So the original intensity, we need to account for that. So how much of that original intensity got reflected? How much of that original intensity was transmitted? Our angle of incidence, so this is our sound beam is not redirected back to our transducer. The beam is reflected in a different direction, and that direction of reflected sound is going to be equal and opposite to the direction of the incident beam. So if we go back to this slide here, the angle at which we are sending in that incident beam is also going to be our angle of incidence when we're talking about obliquity. Okay, so yes, and our angle of incidence is our angle of reflection. So we are going to talk about refraction in a second, but here you can see our boundary here, right? And we have our incident sound wave coming in here. A portion of that, because we're coming in on an angle, is going to be equal and opposite to the angle that we sent that sound beam in. So we're not going to get that reflection, but a majority of that is going to continue traveling forward. Now, depending on that boundary, because we came in on an oblique angle or an incident angle, is going to change direction, and that's going to be our refraction. So this is when we have that change in that wave's propagation as it's traveling from one media to another. This only will occur with oblique incidence. This will never happen with normal incidence. We have to have different propagation speeds of the two media. So a little bit different than impedance. The impedance is the overall resistance of the media. The propagation speed is how fast that sound wave can travel, the velocity of that sound wave in that media. So it has to have two different propagation speeds, not necessarily talking about impedance here. If transmission occurs and these two conditions are met, meaning that we had an oblique incidence and the two media have different propagation speeds, the wave will never travel in a straight line and it will slightly bend. So that angulation and that difference in speed is going to kind of cause the direction of our sound wave to kind of curve a little bit, and it's going to be a little bit more unpredictable. So when we have two media that have similar propagation speeds, so we have a soft tissue and a soft tissue, but we came in at an oblique incidence and those two soft tissues still have those different propagation speeds, we're going to have a smaller, less noticeable degree of bending or refraction. When we have greater interface differences, right? So the speeds are ridiculously drastic, bone versus soft tissue, we're going to have greater amounts of refraction. So we're going to see greater differences in the pathway that that sound beam continues to transmit through. So similar to that previous diagram that we were looking at, we have our original incident angle coming in here, right? So we're not at a perfect normal instance. A portion of this would be reflected, right? But the majority of it is going to continue traveling. But because our medium 1 and our medium 2 have different speeds, and we came in at an angle, it's going to have a slight bend to it. And that's our refracted angle. So let me erase that little drawing down here. I'll erase a portion of this up here. But do you see how that transmitted sound beam is no longer traveling in that perfectly straight trajectory from the original incident ray? It's coming in and kind of traveling off kilter a little bit, right? So this would be our angle of refraction. And lastly, we have Snell's law. So this is something that your registry will definitely ask you about. I don't get too in-depth with it, but what this is doing is it's trying to quantify that concept of refraction. And this is where we get really back into those, like, you know, high school mathematics where we have sine and cosine and all of that. So sine is a unitless number with a value of 0 to 1. We take the we take the speed of each medium that we're talking about in terms of refraction, and we compare that with sine, and I'm not going to ask you to calculate this equation on a quiz or on a test, but just know for me that Snell's law is the mathematical equation that we can use to quantify the concept of refraction. Be aware and remember that refraction needs to have those two components. It needs to have oblique incidence, and the two medium have to have different propagation speeds. Propagation speed is different than impedance and resistance. So a lot of new information on this PowerPoint. Any questions about any of this, please feel free to reach out to me. This quiz also for this module will be due on Sunday as well, so you'll have 2 quizzes due on Sunday. I got my dates wrong for last week's quiz, so you had 2 weeks to kind of do that. Any questions, please feel free to reach out to me, but otherwise you guys are all set, and I hope you have a great day at clinical tomorrow.